I started out as a sorcerer's apprentice, and I worked my way up to being a mad scientist. And these are a few of the steps along the way. What I learned doing that, first, that you have to work the waves. Now, we could spend the whole seminar just talking about tech waves and all of the aspects of them. You can't ignore them, never stop, they keep coming. You can't be too early, can't be too late. So a surfer actually can choose which wave, but in tech we can't. If you miss a wave, you can wipe out. Second thing I learned is you have to own your IP. You have to own your intellectual property. And we can talk about all the reasons for that. I did one thing where I worked for a company, Bank of America, that didn't know how to file a patent. And somebody stole the technology. But that wasn't the worst thing. They implemented it, and they implemented it badly. And so they convinced the world that it wouldn't work. So the really bad things can happen if you don't own your IP. So I'm going to give you a few examples of people not owning their IP. When I was in my early teens, this is the late 1950s, my family had a family friend who was an optics engineer. And he asked me if I would help him become a lab assistant in his optics lab in his basement at home. And I said, sure. Well, it turned out I had two jobs. The first was never look down the throat of the laser. And the second was to keep him company and every once in a while hand him a screwdriver. He told me that he had invented the gaseous planar laser, which was the first form of lasers. But he didn't think they were important, and he hadn't bothered to patent it. And so he was scrambling to try to catch up. There's a famous story about Western Union. Western Union was the first electronic communications, really large-scale electronic communications network in the United States. Alexander Graham Bell went to Western Union and said, I'd like to sell you the patent on the telephone. Western Union said, well, we don't think anybody wants to talk. All these business people want a written record. And no, there's no value in the telephone patent. No, thank you, we don't want the patent. They continued that process of not paying attention to the technology waves and not doing anything to capture intellectual property. And when the ASCII dial-up modem came along, Western Union, as a communications company, dried up and blew away. IBM missed a wave, and they've been shrinking. But they have been very careful to develop and maintain a strong and growing patent portfolio. So the jury's out. We don't know in the long term whether they'll survive, but they have a better chance. Now, it's just not me that's been a sorcerer's apprentice. Andy kind of gave a little introduction and some examples. Oh, first I should talk about Qualcomm. Qualcomm actually did do both of those things. And one of the examples is Qualcomm built a patent portfolio based on CDMA, and that's how they founded the company. But they saw that the technology wave was coming and that OFDM was going to replace CDMA. And this was long before it actually happened. They saw it coming. They went out and bought a small technology company that had a OFDM patent portfolio. And they brought that portfolio in. They had the people in that small company train their CDMA engineers in how to design OFDM systems and focus on building and growing that patent portfolio. And without that, Qualcomm wouldn't be here today. And they successfully managed both the wave and the intellectual property. Now, I said I was a sorcerer's apprentice. Do you remember the story about the sorcerer's apprentice? The sorcerer's apprentice is given the job of cleaning up the lab and decides to use the technology, which is spells, and every time, and it happens to be a male, every time he does it, he either creates another problem or another set of opportunities, and then he has to do another, and it keeps going. And he has layers upon layers upon layers of spells. Well, the same thing has happened in our large-scale systems. And Andy made a distinction between networking and computing. In my view, there is no distinction. We do not have a large-scale system that does not have both communications and computing. And there are people who look at the inside of a microprocessor and say it's all communications, it's not computing anyway. So you can, rather than have an argument about which is which, let's just say that networks includes both. So we have these large-scale systems, and there's layers upon layers upon layers of historical technology. In the financial services industry, we have code that, and it's not compatible, and we run old operating systems because we have code that was written in assembly language 50 or 60 years ago that nobody knows how it works, there's no documentation, and the operation is don't touch it, leave it alone, cross your fingers, we'll just hope that it works. And it's kind of like magic. We really don't know what's there. And you know, your financial transactions rely on that. So we have these layers of technology, but then we also have vendors who want to differentiate their products. And so we have these proprietary systems. So we have layers of proprietary systems, layers of technology, and then we have to combine things to make the function that we want. And if you look at our systems, our large-scale systems, they look like colonies of single-cell animals. Each little subsystem works very well within its own little subsystem, but when it's trying to be combined with other subsystems, you know, kind of maybe they work, but they require a lot of manual intervention to keep them running, and they're not flexible. They're brittle, they break, they crash, and they're not efficient, and they're expensive to operate. So what can we do about that? Well, biology faced the same problem. We look at the evolution of life on the planet. We went through a stage of evolution where the most complex forms were colonies of single-cell animals. And they worked much better than a single-cell animal, but they didn't work very efficiently. They had all of the same problems. They were brittle, they were unreliable, and they were inefficient. And they couldn't protect themselves. They had security problems too. And so what did biology do about this? Biology developed two overlays. One is the nervous system, and the other is the immune system. And the nervous system is based on this idea of distributed intelligence. We call them ganglion. So I'm standing here right now, and in my toes, right down in my feet, there are ganglion. And they're receiving signals from sensors, and they're sending signals to the muscles to keep me from falling over. I've got them in my legs, etc. If all those signals had to go from my toes to my brain and back to my toes again, I'd be lying on the ground before they got there. So the idea of ganglion and distributed intelligence is important. Of course, there's a central intelligence too. We've got the brain. And then the immune system. So we have skin, and the skin is designed to keep bad stuff out, and it keeps 90 some percent, 98, whatever you want to say, 99, 97, 96. But there's so much bad stuff flying around that we know that bad stuff is going to get in. And so the immune system is designed to find it and take care of it when that happens. And it also has a distributed functionality, lymph nodes. So if you think about how could we build systems, how could we use what we learned from nature to make our systems operate like a single multi-cell animal. So, and why do we want to do this now? Why, this is What's going on now that makes this so critically important? Well, financial transactions are important. Making sure that accounting systems work is important. But if something goes wrong, you can take some time to fix it. If you're driving an autonomous vehicle, maybe you don't have time to fix something if it goes wrong. If your whole house is being run by some combination of smart systems, it could be deadly if things go wrong. So as we go through the softwareization, this wave of software now running so much of our lives, the systems that support it are critical. And we cannot be so laissez-faire about them. They have to be reliable. And the other thing is, of course, if they're going to be as widely deployed as we want them to be, and if we're going to have a reasonable standard of living for people on the planet, the costs of operating them have to be manageable. And this is happening in the context of a fundamental change in cybercrime. So we have, we started out with kids in the basement having fun trying to break into systems. Now we have organized crime. And there's lots of different ways. Some people say organized crime doing cyber attacks generates more money than the entire illegal drug trade on the planet. Other people say it's the largest industry by dollar volume on the planet. Pick your numbers, it's big. And nation states decided that was too much a fun game, and so now we have nation state actors. And then we have, just like we had the pirates in England and France and Spain back in the 1500s and 1600s, we have nation state sponsored hacking organizations. So we have very sophisticated attackers. So I'm going to talk today about material covered by a patent portfolio. It's the portions of the portfolio that I can talk about are the portions where the patents have been granted and where they have been published. Patent authorities typically at a certain point, and they have different rules about how and when to do this, publish a patent application while it's under active consideration. And at that either point, granting or publishing, the information is open to the public, and therefore I can talk about it. So what we'll discuss today is approximately half of the portfolio. So here is an example of that kind of kludge I was talking about. This picture was developed by 3GPP. It is the architecture for 4G. Now, there's a little box over on the left-hand side labeled UE. That's user equipment. In a large network, there's 100 million of those pieces of user equipment. There's someplace between 100 and 200 of these large cellular networks on the planet. There's another little box there labeled eNode B. eNode B is a fancy name for a base station. In a 100 million subscriber cellular network, there's 1 million base stations. Every one of the lines on this picture is a simple line, but it isn't really a line. There is a whole communications network underneath that. So there's routers and switches. There's, it could be plain old telephone system, twisted pair. It could be T1, T2, T3, T4, T5. It could be coax. Could be fiber optic. Could be microwave. Think about every form of communications and computing technology that's existed in the last 60 years, it's in those little lines. And this isn't everything. So on top of this, there's a system called OSS, Operating Support System, which has several dozen subsystems. And there's another system on top of all of that called Customer Support System, which has a whole bunch of subsystems. So this is an example of one of these large, complicated networks. Now, just to make it a little more messy, this is 4G. Today, in most of everyone that I know of who runs a really large net, well, no, I shouldn't say. There's a few in developing countries where this is not true, but every large network in a developed country runs 2G, 3G, and 4G. So there's 3 versions of this, 3 different versions, non-compatible versions running on top of each other, embedded in this whole thing. So how do we make this operate like a single multi-cell animal? So the first thing is we have to overlay a nervous system on it. Here is a nervous system. It has 2 components, orchestrators. There's an orchestrator associated with each subsystem within the span of control of this system. It is the primary mechanism by which operations staff, NOC is Network Operations Center, talks and controls. It is the mechanism by which data is exported to other systems or imported from other systems. We'll talk about what the orchestrators do and how they're set up in a minute. The orchestrators are created and their configuration is managed by the conductor. And that the conductor can have some global functions, but its primary function is to create and configure the orchestrators. The orchestrators operate based upon objectives, algorithms, and constraints. Each one has their own set of objectives, algorithms, and constraints, and they interact with their neighbors using this process of objectives, algorithms, and constraints. Now, in order to do that, they all have to speak the same language. They have to have, every one of the subsystems has a different data model and has different sets of interfaces. So we have to create a meta model. We have to translate all of those underlying models into a consistent model that we can work with across the whole system. But we cannot a priori define what that meta model is, and it won't hold still. Because every time we add a new type of device, a new technology, a vendor does a software upgrade, they're going to add and subtract data elements. So we have to be able to make this meta model change, and we can't shut the system down to do maintenance. You know, when you have Mexican food and then the next meal is Chinese food, you don't shut your body down to do database maintenance. You have a way of dynamically reconfiguring yourself to take advantage of the new environment. The system has to be able to do that. Also, there's the amount of data involved in this, because all of these different little systems are just constantly, there's all kinds of log files, there's all kinds of operational data. And if you try to collect all that data and you try to collect it in a central site, you end up with too much data. And it's too old. By the time it gets to the central site, it's no longer, relevant. So instead of doing that, you want the system to deliver just the data that's needed, just where it's needed, just when it's needed. So those are kind of and then there's the process by which the orchestrators work together. There has to be an old brain process and there has to be a new brain process. The old brain process is the reflex process. And so there are certain things where If A happens, you have to do B. So you want to be able to implement those kinds of reflex processes, and you'd like them to be able to operate across multiple orchestrators. So when I hit your knee right under your kneecap, there's a sensor. Think about an orchestrator attached to that sensor. And then there's an orchestrator attached to your muscle that causes your leg to go up. That's a reflex. Well, so we could have similar kinds of things happen here. But there's going to be things where we don't know what's going to happen, and we don't know exactly what the right thing to do is a priori. And so that's got to have a new brain process by which we can analyze the environment and make decisions that are right for that particular circumstance. So that's what the process means. Now, we've implemented this. This is a demonstration of a macro cell system. I didn't talk about the fact when I showed you that spaghetti diagram, there's a million macro cells. There can be right now like 250,000 small cells. When 5G is deployed, there could be 5 million small cells. But anyway, this is macro cells. Typically, oh, by the way, it costs a network operator like Verizon 10 times as much as the equipment cost just to install and provision. In other words, to install and configure a base station in the field. And it can take months. And so what we see here on the top layer, we have this OSS. I didn't tell you, I said OSS and customer support system. There's also a business support system. I mean, there's systems upon systems upon systems, and they all have little bits and pieces. We've got two here, an inventory management system and a configuration management system. And they're by different vendors. And they're incompatible. And how do they get tied together today? By human beings. Operators have to take the output of one and put it into the other. And when you're talking about millions of things, you can think about what that means. Now, the particular system that we did this was specified by a group of the largest cellular operators in the world. And we had Juniper providing the interconnection. And then ZTE has two different divisions in two different parts of China. And they might as well be speaking different languages and be in different countries because they don't design systems the same way. They don't understand each other. They don't have interfaces that work with each other. And oh, by the way, one product line in one of these divisions will not be compatible with the next product line because everybody's got a better idea and things keep constantly changing. So part of what vendors do to try to help manage this chaos is they build what are called element management systems. So here's another layer that wasn't in the spaghetti diagram. So ZTE has an element management system for all of the core components and another element management system for all the base stations. And you can imagine if a network operator has 3 or 4 vendors, there's going to be 6, 7, 12, a dozen of these in every data center, and there could be 3, 6, 12, pick your number of data centers. In China, there's one in every province. So it could be like 52. And when the use case here was to have an existing network with 2 macro base stations and you want to add capacity, so you put a 3rd base station in. When you put a 3rd base station in, you have to install that base station, you have to provision it, but you have to reconfigure the other 2 base stations so that they all don't interfere with each other. And the base station that you install, you also have to configure all of the communications links between it and the EPC, which is the Evolved Packet Core, and all of the subsystems within the Evolved Packet Core. Here we show the Security Gateway, the SGW, and the MME, the Mobility Management Entity. But there's others in there too. And this whole process can take months. And it can cost because we're talking about it 10 times the cost just to go out in the field and install the base station, could be another 10 times that in planning and organizing and getting all of this to work together. And it's all labor. It's all paying people to turn the crank. So we automated that whole thing, and we were able to do the provisioning and reconfiguration in less than a second, and to do it without human operators. Okay, so we did another demo, and this is with small cells. And this is interesting because it shows more of the internals of the system. So UM stands for umbrella model. That's what we call the meta model. And there is, in every orchestrator, there's a bridge function. And the bridge function translates between the interface and the data model of the system it's associated with into the meta model. And each of the orchestrators has all the data about the subsystem it's associated with, but it also has, and it automatically gets all the data that it needs, and it gets it when it needs it, from the neighbors. So it does not have the whole umbrella model. It only has a piece of the umbrella model, but that's all it needs. And instead of talking about applications, we talk about use cases. And the reason we talk about use cases is because they span multiple orchestrators. And we actually did this with real equipment again, so the names of the vendors and stuff is there. Now, the use cases that we did with this, the first was automated provisioning. And what we found is that automated provisioning reduces the installation cost by 50%. So to install a base station, just the guys in the field to do it, costs $100,000. When we do this, we reduce the cost to $50,000 because they can do twice as many base stations in the same amount of time. But then the more interesting case is what happens when something goes wrong. And the thing that goes wrong most typically is what's called impaired backhaul. So this 4G standard has a mechanism for load sharing between base stations in a neighborhood. But it only knows about spectrum. It only knows about the RF space. So when a new UE, when a new device shows up and says, I need service, this mechanism has a way to decide which of the base stations that device, because typically you can see 3 or 4 base stations, which base station you should assign that device to. And it says, okay, well, who has the most unused RF capacity, and it assigns the UE to that device. But if that base station has lost half of its backhaul, everybody assigned to that base station is going to have lousy quality of service. And what happens is, that's what you and I say, oh, we got a bad line, hang up, I'll call you back. So everybody's hanging up and calling back, which wipes out the other base stations in the neighborhood. And that goes on until somebody, and it's a human being again, in an operations center figures out that there's a problem, and then they have to dispatch a truck, there's a truck roll, and so it can go on for a long time. It can go on for months. So if we have an orchestration system where we know, because we have an orchestrator that looks at the backhaul, we know when there's a backhaul problem. So if we can change the allocation of RF capacity such that the base station with impaired backhaul has RF capacity that matches its backhaul capacity, and we give the rest of the backhaul the best of the RF capacity to the other base stations, it's not perfect, we still can do better after we fix things, but while we're fixing things, the whole system will run much, much, much better. So that was the second use case. The problem is, okay, so first we have to talk about how often this happens. In a network of 1 million macro base stations, at any given moment in time, there are 10,000 base stations that have impaired backhaul. Okay, so just think about the manual process. What seems simple to do once when you're talking about 10,000 becomes a bigger problem. So we don't know what the situation is with the neighboring base stations. And we don't know what the right answer is. So what we do is the orchestrator associated with the backhaul lets the orchestrator associated with the impaired base station know that its backhaul has been impaired. That orchestrator then starts a process with the orchestrators of the other base stations in the neighborhood. It says, hey, I need to get rid of capacity. Now, capacity in 4G and 3G and 5G is all measured differently. Just to make it simple, we're going to talk about channels. So I need to give up a channel. Can anybody take a channel? And then there's a negotiation procedure, and one of the bidders says, okay, I want it, so you can have it. And then the orchestrator goes back and says, okay, does my backhaul capacity match my RF capacity? No. So it goes through the process again of saying, can anybody take a channel? And the negotiation process goes on again. Okay, so when this goes until everything gets balanced, when the backhaul is repaired, can you just replay what you've done and just undo it? No, you can't. And the reason you can't is because the situation could have changed. One of the other base stations could have had impaired backhaul. It could have been giving up capacity. A base station can be in more than one neighborhood. It can be passing capacity to another neighborhood. You don't know what the situation is. So you have to start all over again with negotiation. So the base station that now has enough backhaul capacity, its orchestrator says, can anybody give me a channel? And there's a negotiation process, and then through that process, we get back to balance.
Okay, so before we get started,
can you all hear
just
this?
a couple of comments about the environment where we're running. I'm running this demonstration on a Linux laptop with 5 separate KVM virtual machines running on board. And I've got 3 windows on the right side of your screen which show the console logs of 3 of the local distributed orchestrators for the 3 eNode Bs, which allows you to see a little bit of the message traffic and the work that's going on each of those nodes during the provisioning process. On the left side of the screen is a console which was developed specifically for this demonstration. And at the top, I've got a map view which shows the devices that are being managed, which I can also show in a topology view. And what we'll be doing is configuring the EPC and then the 3 eNode Bs, which are associated with that EPC in this environment. And I'll be doing that by utilizing these control buttons on the left side of my screen. When I do that, I'm going to go ahead and start by configuring the EPC. What's going on in the background is that I'm sending a message to its local distributed orchestrator, which says, change your state from defined to configured. And when it does so, it knows how to generate this message, which is displayed in this text view in our umbrella model. It generates this and hands it over to the bridge process running on that same device, which translates this into a series of calls that are made to the exposed API on that device to affect that configuration. And as you see in our display, it changed from yellow to green when that configuration was complete, which took basically less than a second. I'm going to go ahead and configure the rest of the devices now that the EPC is up and running. And when I do so, you'll see that the same process takes place. The umbrella model configuration is generated, the bridge process takes over, configures the device, and now everything's green. Now in this demo, as was explained, we're using this notion of abstract channels, which represents capacity on each of the eNode Bs. And underneath the configuration box, you'll see a list of channels, which shows the initial capacity allocated to those devices. In the use case where we had an impairment of a backhaul, basically what we need to do is have the eNode B, or the orchestrator that's controlling the eNode B, reallocate some of its capacity to the other nodes that are operating in the neighborhood. So I'm going to go ahead and click on the Impair button for eNode B2, at which point in time the negotiation process is started, and that local distributed orchestrator starts to offer some of its capacity to its neighbors, and you'll see the channels being reallocated to eNode B1 and eNode B3. I should mention at this point in time that I've built in a delay in this negotiation process just to allow you to see what's going on. There's actually a 2-second delay in there between iterations of the reallocation process, and that allows you to see the channels move from one device to the other. At some point in time when the backhaul is impaired or repaired, I can restore that device's capacity by clicking on my restore button here, in which case the local distributed orchestrator starts asking for some of that capacity to be returned by its neighbors, and you can see everything rebalances and each of the nodes is running again with 10 channels.
Thank you, Frank.
Okay, so that was kind of a discussion and showing you how a system in a cellular network would work. The same thing can be done in an enterprise network, a government network. Everything is the same except the names of the devices in the little blue boxes on the bottom. They change because it's different subsystems. But the same problems exist and the same solution works. Now, what about security? So, what we want to be able to do is to find those things that get through the external barriers, our access control and firewalls and things like that. And then, of course, we would like to fix them. So again, it's the same system. Everything's the same except the names of the things in the blue boxes change. We're going to talk a little bit about how this works. So the primary mechanism used to figure out if something bad has gotten into the system is what's called behavioral analysis. Behavioral analysis was developed at Stanford Research Institute in the late 1980s. I actually had a chance to work with it in that time. And it was originally focused on what's called intrusion. And so the first systems were called intrusion detection systems, or IDS. But it's all the same. But I'll give you kind of an explanation of how it started. So the idea was to figure out if somebody had stolen somebody else's credentials and was using them to get into the system to do bad things. So user profiles were developed. So Joe shows up in Menlo Park every Monday morning at, Monday through Friday, logs on at 9:15, logs off at 4:45. All of a sudden, Joe appears to be showing up on Saturday afternoon from Shenzhen. Is that Joe? Well, it's a behavioral anomaly. So then you have to do an investigation. But the thing is to capture the fact that it's a behavioral anomaly. And so that's what the behavioral analysis systems did. They would develop a behavior pattern for each user, and then they would alert when the behavior didn't follow the pattern. Now that was expanded to include devices. And anything that has behavior can you can develop this kind of behavioral analysis system for. And right now, typically, the way these things are done, there's a collector. In this case, it's called a security probe. There's a collector out in the field, and the collector collects data. Though there's lots of different ways of doing this. The two most typical are that a collector takes log files from the systems it's connected to. And another way is to capture all of the IP addresses that flow through a system. And because they bring all this data back to a central site, some of these systems are already getting close to exabytes of data, and they have to throw it away. They don't have storage systems big enough. They have to throw it away after a few days or a week. And it can take days to find a pattern because there's so much data you have to wade through. So they try to pick points in the system where they might get the most leverage. And it's quite typical to pick a router or a switch as a place to begin to examine behavior, not only of that switch, but everything downstream from it. And then if there's an alert, if there's a behavioral change, then it goes to a human operator. Now it's called an SOC, a Security Operations Center, and that operator then has to decide if they want to take action, and if they want to take action, what they should do. This turns out not to be an easy job. It turns out that it is financially almost unaffordable to have on staff 24/7 people who know the intimate technical details of every subsystem in your network. Every computer, every application, every switch, every router, every firewall, every access control system, etc. And even if you have the money, you can't find enough trained people to do that. So what happens is that people create what are called playbooks. And it's like a recipe. If A happens, open this book up and follow the instructions. The problem with playbooks is that the people who actually sitting at the keyboard executing them have no idea what they're doing. And if they hit a wrong key, fat finger problem, they don't know how to recover. And so we've seen fat finger problems bring down an entire network. S2 went down for the better part of a day because of one fat finger problem. So what happens is that the security staff scratches their head and they say, what's the risk that if we actually do remediation, we're going to crash the network? And more often than not, they decide not to fix the problem because they're afraid that the cure is worse than the cold. So one organization, one US corporation, has 300 subsidiaries. Each subsidiary has a firewall, at least one, sometimes two or three. They have one of every firewall that's ever been manufactured, ever been sold into the market. They have firewalls that are no longer supported by their vendors that are still running. They got an alert that an attack was coming, and they knew what the IP addresses were that it was coming from. So they could have gone out to all of the firewalls and blocked that IP address and not let anything in from it. But they decided that if they did that, the risk of blowing up the network was so great that they'd rather let the attack come and try to clean it up afterwards than to prevent it. And this is not an unusual circumstance. This is how, and then what happens, of course, is these staffs, they come to the conclusion, well, geez, if nobody knows we've been breached, everything's fine. So we'll just keep it a secret. And that's what happened with Yahoo. And it only cost them $1.2 billion because nobody can ever keep those things secret forever, let alone the fact that the attackers know that they've done it. So, you're subject to blackmail. So anyway, this is the kind of current situation. So we add orchestrators. We add an orchestrator to the behavioral analysis engine. We add an orchestrator to the SOC. Now, the reason we do that is because, depending on the policy decisions of the organization, they may not want automated remediation to happen without human intervention. So this allows an alert to come to the SOC staff, and then the SOC staff to be presented with, here's an analysis of the problem, here's what we recommend you do, and guess what? They only have one button to choose. They get to click on yes or no. Minimize the fat finger problems, okay? And, but it could also be automated. And then we have an orchestrator associated, in this case, with a switch and a router. And we can see the behavior of the switch and the router and of the downstream devices. And because we have the capability of doing this, we can actually implement the remediation actions. So here is an example. Again, this is from the cellular industry, but it applies, you can imagine how this applies in,
In this use case, we have several small cellular base stations that are installed in Starbucks in downtown San Francisco, and there is a virtual EPC, a controller that controls how those base stations talk to the cellular network. And in this use case, one of those base stations becomes compromised and it's stealing customer information. And that is detected by a behavioral analysis system, which sends out an alert. That alert can either be picked up directly by Orchestral Networks local security engines and acted on directly using rules, or that alert can be presented to a console operator, and that console operator can take action to quarantine the device. So I'm going to assume that it is the latter, and that we had the console operator see the alert and is going to quarantine this first device. And as that happened, you may have seen some text flying by on the right-hand side, and these are basically just console windows connected up to our engines so that we can see the message traffic. And you will also have seen that this window right next to the device got cleared and the configuration was removed. At this point in time, the device can be analyzed. We can figure out what went wrong, how it got compromised, make corrections within our system to the system configuration, and then push out a new configuration to that device and bring it back up online.
Thank you, Frank.
okay, there's many different forms of remediation, and during the question and answer period, we can talk about those if you have questions about them. But we can make this system better. So instead of having a separate collector, we can have the orchestrator also do the collection and deliver data to the central site behavioral analysis system. But we can also have the local orchestrator do its own behavioral analysis. And we can do this with an extremely small footprint. We don't have to keep all the data. So part of the problem in the central site system is that the central site system has to keep all this data, and it's a huge big bucket of data, and then it has to wander around in that to find anything. But it also has to have a lot of human people telling it what to look for. It's not, this is not the idea of finding patterns with neural networks. People try to say that, but in security kind of things, it doesn't quite happen that way. And we don't want the orchestrator to be this big, huge thing. We want it to be really small, and we'll see how small we want it to be soon. So we have another mechanism, and the way we do this is we create histograms. And we create histograms without any understanding of what the parameters mean. We don't really care what the parameters mean. All we do is we take a statistically valid sample and we create a moving sum average. So we constantly update, and we don't keep the data, we just keep the histogram, and it's just one histogram, and it's just updated, and it's constantly kind of going through whatever small change. And if there's a big change, then there's an alert. That's a behavior change. And with that, we can deploy this out to the edges of the network, and we can still run the central site system too. We could do either or. There's another thing here. We have some threat intelligence systems. So that US corporation I told you about that had 300 subsidiaries, they subscribe to 156 threat intelligence systems. So those, each one has a different interface. Some send email, some are push websites, some are pull websites, some are paper. And they all have different, some send out stuff every minute, some sends out stuff every hour, some every day, some every week, some every month, et cetera. In that corporation, there's one person, and it's not his only job, it happens to be a man. It's not his only job. He has to run the whole security operation, who reads 156 threat intelligence reports a day and decides what, if anything, to do about them. So, again, you can imagine what that means in terms of time and effectiveness. So we put an orchestrator out there, and with orchestrators, we were able to actually make that threat intelligence information actionable. Now, in an enterprise, typically enterprises also have layers of history, because of mergers and acquisitions and reorganizations. So they don't have one of anything. And in their security environments, they have lots of firewalls, lots of access control systems, lots of behavioral analysis systems, lots of element management systems. Of course, lots of routers and switches and lots of clouds and lots of, there's something up there called a SIM, which is supposed to kind of try to keep track of things, but they have lots of different versions of those. And how is that all held together? Again, it's either not held together or it's held together with manual effort, which is expensive and slow and scale not effective. So we replace it by or enhance it. We don't replace the operators, we enhance the operators by deploying orchestrators for each of the systems. Now, what about a cloud? Well, typically today, cloud systems have a behavioral analysis engine and they have a data collector, but typically the collector is collecting data on the cloud as a whole. And when you do that, what happens to an individual application can be lost in the detail, in this flood of information. And the other problem is that those applications are moving. And what happens if the application moves from an internal private cloud to an external public cloud where you, the organization that is running the application, do not have a behavioral analysis engine, or you don't have access to the third-party provider's behavioral analysis engine. And maybe it's not compatible with yours. So the answer is we put an orchestrator, we associate an orchestrator with the app, and then the orchestrator moves with the app. The orchestrator then has a behavior pattern that's unique to the app, and it can see when the app is deviating from its normal behavior. And it can see that regardless of where the app is running at any given moment. Well, how about vehicles? Well, we have a car shown here, but it could be a boat, it could be an airplane, it could be a drone, any kind of vehicle. But let's talk about cars as an example. So cars today have a component called a telecommunications control unit, TCU. And that TCU handles all of the electronic communications to the outside world. Oh, by the way, do you know that there are more cars stolen in the United States today by hacking the control system than there are by physically breaking into the car? Yeah, just interesting kind of to see how the world's changing. Crime, criminals are pretty good at being dynamic. Our systems are not as good as being dynamic, and that's why we need to have this kind of capability. Okay, so we could put an orchestrator just on the telecommunications control unit, and we could observe the behavior of the TCU, and we could observe the behavior of everything downstream. But of course, in doing that, there's some latency issues, because whatever's happening downstream, it's going to take maybe a second for us to find out about it. Do I care about a second? Well, Audi is selling a version of the A8, which has an autonomous driving capability. The capability is such that it will be engaged if and only if the vehicle and the traffic around it is going at 30 miles an hour or less, and it's on a divided highway. If either one of those conditions are not true, it doesn't change lanes, it just stops, and it turns on its flashers unless the human operator takes control. Now, when Audi sells the vehicle, they sign a contract in which they say they are responsible, financially responsible, for all accidents that happen when that vehicle is in autonomous mode. Do you think Audi is willing to let something go wrong with inside the car and let it go on for a second or two before they find out about it? Okay, so inside the car are a whole bunch of other control units. There can be as many as 50 of these control units. I just made up some examples. An engine control unit, a steering control unit, a braking control unit. You can decide how you want to associate orchestrators with the control units. You can go down as far into detail as you want. These are, remember, they're very small. They have an extremely small footprint. And now we have another entity, fleet operations. So in the Audi example, I'm an individual consumer, I buy an Audi A8. But from a security point of view, Audi is still the fleet manager. They're going to keep track of that car to make sure that they don't end up with financial responsibility for an accident they could prevent. Okay, so now we have these two systems. We have the nervous system, the ganglion, and we have the immune system, the lymph nodes. What happens if we combine them? Well, there's some things that we can do that we couldn't do before. So for example, right now, if I'm a cellular network operator, I have to decide where to put my base stations. And that's why I may spend 6 months going through an analysis before I put a base station out there. It's a big expense. And I have to hope that I get enough base stations where the traffic is, because otherwise bad quality of service and my customers go away. And I want to make sure I don't have too many base stations where there's no traffic, because it's too expensive. So I'm constantly trying to figure out how to do this. Well, what would happen if we put the base stations in a vehicle and the vehicle went where there was a demand for service? Well, they can't do that today because it takes them, pick your time, week, month, whatever, to reconfigure the neighborhood when you add another base station. But we can do it in less than a second. So as the vehicles move around and we can reconfigure the cells so that this whole thing becomes dynamic. Tremendous improvement in efficiency. And then the question is, well, what about the security, not only of the vehicles, now we got a base station in the vehicle, but how about the users inside the vehicle? And by users, I mean UEs, right? User equipment. Can be, we really don't care what it is. So we can provide kind of a zone of security so that there's security inside the vehicle, and we can make it at the same time become a base station that moves to where there's a need for the base station. Okay, so everything we've talked about up until now has been about big systems. But if you look at what's going on inside single semiconductors, single chips, it looks pretty much like a big system. It's, we've got SoCs now, a network tying all of these separate little cores together, and typical size of an SoC today is 30 cores. People in the industry are talking about 300 cores. People in academia are talking about 3,000 cores. Now, there typically is a component inside the SoC that's responsible for external communication, off-chip communication. Doesn't have a standard name like TCU, but so we could just put an orchestrator there, and we could look downstream at everything going on inside the chip. And we can do this because we have this, the orchestrator is such a small thing. Now, to do this, you can argue about software versus hardware. It doesn't matter. It's complicated to talk about how to do the software solution. But adding a very, very small component inside a chip is, there's plenty of room. We've gotten feature sizes so small now that people are trying to figure out what to do with all the real estate. And chips now are pad limited. The number of external connections determines the size of the chip, and so how do you make good use of the real estate? So there's room in here to put orchestrators. We could put the orchestrators, associate them with individual SoC cores to make sure that the core is behaving correctly. Now, in the last year or two, we've had this whole set of concerns come up about called, well, a friend of mine, he's corrupted me, he calls it smelter down. But that has to do with in-chip, in-processor vulnerabilities. John Hennessy gave a talk a few months ago here at EE380, and he said two interesting things. First thing he said was, there's a new one of these vulnerabilities being discovered every month. Second thing he said was, he, John Hennessy, could, in the process of designing a processor, put a backdoor into the processor that you would never find. And he guaranteed he could do that. And I believe him. And I don't think he's the only one who can do that. And there's some indication that that's been done, and there's some tension going on between governments and vendors, which you guys can all fill in the blanks. Okay. So, can we predict all of the vulnerabilities? No, we cannot. Can we close all the vulnerabilities? Well, in Smelterdown, the answer was yes, we could close all the vulnerabilities if we went back to 1990 performance. And everybody said, no, don't take us back to 1990. So how do we keep performance and have security? Now, how important is this in-processor vulnerability? Well, to use it, it takes a sophisticated attacker. Do we have sophisticated attackers? We have nation states, we have pirate groups, we have organized crime. Are they sophisticated enough? Yes. What is the consequence of having these vulnerabilities? I really don't want to go into it in a public setting, but it is possible, using these vulnerabilities, to exfiltrate data from any application running in any public cloud anywhere in the world today. And it's not hard for a sophisticated person. So it's a serious, serious, serious problem. So how can we solve it? Well, if we put orchestrators in the key places, and it has to do with how data moves inside the chip, inside the processor, we can, and the orchestrators have to be very small, but we can make them very small. Remember, we're not storing a lot of data, we just have this histogram, and we really don't even have to know what that little piece of the puzzle is doing. All we have to do is be able to establish what its normal behavior is. Then we can tell if somebody has intruded, invaded, somehow is exfiltrating data, or forcing control actions which are unauthorized. And if we see them and we can see that that's happening, then we can take remediation steps. So, as you've got a feel for this, I didn't really cover everything because we didn't have time. Also, sometimes it's overwhelming to put everything in one fell swoop. But it's a very generalized solution to these kinds of problems. And these problems exist in smart home, smart office, smart factory, smart highway. There's a problem in SoC design and operation that has to do with combinations and permutations. The A5, there's a joke in the community that the A5 was called the A5 because it took 5 years to develop. That's Apple's A5. I can't get a laugh out of this audience. So the technology can be used there also. How do we move? Each one of the major vendors wants to lock us in. We get an application running in their cloud. In fact, we have a private cloud. They want us to buy their cloud software, to run their cloud software in our data center so that we can move from our data center to their public cloud and back and forth. They want to lock us in, so okay. In combinations of information from incompatible systems, if you know about health record systems, in San Diego County, there's the Army, Air Force, Marines, Navy. Each one has a separate medical system. There's the Veterans Affairs. Each one has a separate medical system. There's the county medical system. There's the University of San Diego Medical Center. They have a separate system. And then there's all the private practitioners, and they all have separate systems, and they're all incompatible. And one person or one family could actually see every one of those in one day. So how do that's like when you go to the doctor and the doctor says, are you sick? And you say, well, I came here to find out. And they say, well, but we don't have the records. Tell us, So we become the walking information system. It doesn't work very well. There's also implications for standards. Instead of trying to specify everything, leaving stuff up to negotiation, there's an article here that's been published in December. You can look at if you're interested. The technology is agnostic. It doesn't matter what the underlying technology is. These are the granted patents and the in-process published patents that cover stuff we talked about today. And in conclusion, it's why? Because it's time. Why is it time? Because of the reliance we have as a society and the increasing reliance for life on these systems. How do we make them? We got to make them work better. How do we do that? We make them work like, instead of colonies of single-cell animals, a single multi-cell animal. And to make sure that it gets done right, we need to make sure that we have control of the intellectual property. Okay, if Andy will allow me, well, I'll be happy to take questions. Thank you.